So what is the nature of the insulating state? What are the possibilities? It's not a band insulator. Is it an Anderson insulator localization by disorder because the samples have some degree of disorder? But we do not see any finite DOS at Fermi level, so it's not Anderson insulator in that sense. But to argue that this is Mott physics, one should realize that this is very high doping compared to, say, copper oxides or other things. This is 50% doping, way overdoped. So charge order, it's 1/2, so it cannot be commensurate. One possibility is that, consistent with neutron observation, that this antiferromagnetic stripe order, it leads to some sort of nematic type charge order, which is possible at 1/2. So this is, but commensurate charge order is not possible. And of course, this broken symmetry induced by the sodium order is a perturbation to the system. So I do not have a final answer. What is this state, or what is the nature of these phase transitions? But one thing I can say confidently, that this is a rare case where quasi-particle coherence is driving setting the phase transition scales.
Why do you say that? So I don't understand.
Because.
Sorry, are you saying? Make sure I understand what that's where I mean that you don't see the quasi-particle above where the CDW develops, and once you go into the CDW, the quasi-particle shoots up.
Yeah.
But that's a different statement than saying it's driving necessarily.
No. Yes, Yes, I agree. What I mean is that it's setting.
The recuperates, I mean, at least an underdosed.
Yeah.
No quasi-particle, you go into the superconducting state and you get a quasi-particle. So,
yeah.
I don't know.
I
don't want to say there that it's driving.
Right. No, I agree that driving is not the right word. It's that is setting the energy scale when that happens.
They coincide.
Coincide, yeah. Yeah. Well, I do not know what is driving. That is the mystery, right? So I do not know what is driving the phase transitions, but it seems like quasi-particle coherence is an important player.
Is there a symmetric change across the metal insulator transitions?
Not known from X-ray or neutron scattering. You mean the crystal structure? No, there is no structural. No, that is the biggest mystery. There is no magnetic change. The stripe order parameter, Young, Lee, and other people have observed, it doesn't care about the metal insulator transition. It's unnoticed by.
Is it second order or first order? Probably picks up some of the letters.
The metal insulator transition. It's not very hysteretic. I mean, so it's probably not strongly first order. If you do temperature cycling, it's at the same temperature. I haven't seen anybody claiming it's hysteretic.
Does it have large thermal power?
Yes, it has large thermal power at low temperature.
Oh, how about high temperature?
High temperature, large thermal power is in all doping. It's not specific to this particular composition. Yes, it has large thermal power in all doping.
So it's almost classical thermal power.
Yes. Actually, no, it's more than that. It's 10 times more than the classical thermal power.
No, it's classical in the sense that it's KB over E, not suppressed by temperature or something.
Right, it saturates to some value. It's close to classical value.
This potassium compound, what is systematics with X?
It has all these transitions, except that they are shifted.
No, with the composition, does it have Curie-Weiss metal?
Oh, that potassium compound is not stable in either side of the phase diagram. You cannot explore it further. It's only near 0.5, yes. Okay, so the second topic is Dirac physics beyond graphene. Okay, so some of you might know there is a paper in Science Express which seems to claim that there is fractional quantum Hall effect in pure three-dimensional bismuth. And I found that very puzzling because my limited understanding of fractional quantum Hall effect is it requires some sort of two-dimensional electron gas, but that may not be true. So motivated by this, I worried, is this finding related to some hidden surface state in bismuth, which leads to this fractional quantum Hall effect? If you look at the bulk band structure of bismuth, it's very much three-dimensional. So it's a puzzle. Is this fractional So the question I pose is that, is it related to surface states? And that's something I can measure with ARPES. Now, if I look at the reciprocal space, it has a rhombohedral 3D structure, and one can see it has many faces. So this is the 111. It has many other faces. So in order to confirm that the fractional quantum Hall effect observed in bismuth has to do with a surface state, I have to look at all the surface states and get the electron density and all that and correlate it to the field where these Landau levels are observed. I mean, these fractional levels are observed. So, but there is a challenge here. The challenge is that this bismuth will not cleave in all surfaces. So the best cleave you can get is on 111 surface, and if you're lucky, you can get a cleave on 110 surface. Other than that, it's not easy to cleave. So we decided to explore 111 surface in some detail.
Is bismuth not famous as a semi-metal? Or?
It is a semi-metal, yes.
So it is quite particular, right?
It's Landau's favorite metal. I think even Landau or people after him, they tested Landau theory on bismuth. And bismuth was the first metal ever in solid-state physics where Fermi surface was determined experimentally using quantum oscillation experiment. It's well understood into the 60s. But yes.
What's close to being a semi-metal? Is that what you're saying?
It's close to being. It has a small Fermi pockets. Yes.
I mean, how small are they?
Very small. It's so small that if you were to get a quantum Hall effect, you could do that with almost room temperature. I'm sorry, in a lab source, like 10, 20 Tesla.
So I see, so it's...
Carrier density is very low.
I mean, it's tiny. I mean,
Very,
yes.
Yeah. So you jumped ahead in my case, but it helped my point, is that if I measure the carrier concentration on the surface, as pointed out, it's very large. So you cannot get fractional quantum Hall effect from this surface at this concentration. So I ruled out that 111 surface is not responsible for creating the fractional quantum Hall effect in bismuth. But then I cannot do more than that. But I found something more interesting. Now I'm off fractional quantum Hall effect, but I found some other quantum Hall effect. So as it has been pointed out, bismuth has been, and its alloys have been studied to death since the 60s, mostly by the Russians, and there are enormous review volumes you can find. So it turns out that if you dope or alloy it with antimony or tin, you'll get some sort of semi-metal to semiconductor transition. And so we decided I suggested my colleagues to grow these samples, and we decided to explore the system in more detail with a modern outlook. So what we see is that if you dope it with antimony or tin, then you get a very large resistivity into the semiconducting regime, and it does have a gap, as I will show. It turns out if you look into this Russian literature, then they could never resolve whether the saturation is due to imperfections or it is an intrinsic effect, because nobody has ever found a pure insulating state in bismuth-based compounds. And that I'm jumping a bit, that I think it has to do with some surface state, metallic surface state, which is topologically protected, which always contributes to conductivity.
With 10% antimony, was it? I mean, what does it go in an ordered way? I mean, it's some.
It's disordered.
It's just completely disordered.
It is disordered, yes. Okay, so even if it is disordered, its electronic structure is very clean. That disorder, I'm getting into that. So if we cleave 111 surface, right away we can get a surface state, very clear. And you have large Luttinger volume here, so it's much larger than what you get, what is in bismuth, carrier concentration in bismuth, so you know that right away it cannot be bulk representative. So this Fermi surface is surface state. So but I need a critical check. Just as in sodium cobalt oxide, we have done systematic work to find out what is the surface effect, what is the bulk effect. In this case, we did a similar check.
What's the first surface here exactly? What's
it's okay. We'll get into okay. So you have a pocket here, another pocket here, the pocket here. So I'm now doing a 6-fold symmetrization. I haven't measured those things, those part of the Briand zone. So you have a lot of pockets. So you have 6 pockets. So this is hole-like, this is electron-like, this is electron-like. So you have 12 pockets, 13 pockets on the surface state.
Is there any change in the physical structure when you do it with antimony?
No. Crystal structure is not very sensitive to that. Well, your lattice constitute change, but no symmetry.
And antimony is directly above bismuth on the periodic table, is that right? Also,
yeah.
3p electrons.
Right. Yeah. So in this case, antimony goes to the same site, right? Because it's alloying, not. Okay. So if I take it, how do I get that surface state? Well, I mean, I want to check if it is surface state or bulk state. There are systematic recipes how to check that. So if I take this cut from gamma to m bar, so I see this band, this band, this band. I see all these bands. And I also see a weak trace of band here. And one can see that it's quite rich. So I have, I'm getting, so this is the M point. So this Fermi pocket or Fermi arc is coming from this, and that part, this is coming from that. Okay, so if I take a cut perpendicular to it, then what do I see? I see this, if I go through this, I see some intensity here, then very much linear bands. And the Fermi velocities are so large, and remarkably, they're almost similar, same as graphene. This Fermi velocity is just same as graphene. So, but just if I take a graphene spectral function and compare it here, it will look like this is electron-doped graphene, because you have electron. Now, so I suggested my colleague that let's suck out some electron from this system, so we'll get a Dirac point. So he tried that, but he can never get, and we repeatedly measured the samples, but we can never get rid of this thing. So in other words, it's something else. It's not doped electron in a graphene-like band structure. It's something else. But this linearity is quite remarkable, and somehow it has the graphene-like velocity.
Could you remind us again of what value of kx that scan was?
This scan?
Yeah.
This 2, number 2 correspond to.
Okay.
Yes.
But is there really a cone?
Yeah, I'm getting to that. So